Last video of Chapter 8 is calculating confidence intervals for a mean difference, aka we're going to be dealing with something called matched pairs, which should be something familiar to you. Back in the day, we used to do a matched pairs design when we were designing experiments. So the whole idea of a matched pairs shouldn't be a foreign concept. And what you'll find out is all the math for doing a matched pairs confidence interval is exactly the same as it is for just doing a normal one mean confidence interval. Now, instead of having a special guest for this video, I thought maybe we'd switch it up here. And this is going to be sponsored by Masterpiece Theatre on PBS, you know, Downtown Abbey and all that stuff. So here is the video in Masterpiece Theatre language. So we may also put in a British spin into it, but mostly Masterpiece Theatre. We are going to be fancy with our statistics today. So, a matched pairs design. So here are some examples of a matched pairs experimental design. We could say two seeds of the same type of plant are planted in the same pot. One is randomly selected and treated with a new fertilizer. The other seed serves as the control. We want to estimate the mean difference in the growth of 10 such pairs of plants. An elementary school teacher uses a matched pairs design when giving a pre-test and post-test and then determining if the students improved. And a study tries to determine whether the caffeine addicts are more depressed when they receive a caffeine placebo rather than a caffeine pill. So what makes an experimental design a matched pairs? Well, each person receives both treatments, or each treatment is given to one subject in each pair. Now, if we do it more this way, the two subjects must be pretty similar to each other to begin with, maybe twins, or they have been predetermined to be very similar in some respect. So when we were talking about the plants up here, obviously we cannot do it to the same exact plant, but we were doing it to the same variety of plant. The elementary school teacher used the same student with both tests, a pre-test and a post-test, and giving the same subject a placebo pill rather than a caffeine pill. So they receive both treatments. Now, how do we analyze a matched pairs data set? Instead of looking at the two sets of data, we are going to look at the observed differences of those two. So we're going to create one set of data where the data are the differences of our two things. So the example we are going to look at. Our subjects are 11 people diagnosed as being dependent on caffeine. Each subject was barred from caffeine, colas, and other substances containing caffeine. Instead, they took capsules containing their normal caffeine intake. During a different time period, they took placebo capsules. The order in which subjects took caffeine and the placebo was randomized. So they did not want each person to always take the caffeine pill and then the placebo pill, because that would be a confounding effect. We would not be able to differentiate the caffeine and the placebo if they were all giving in the same order. One of the tests given to the subject was depression, as scored by the Beck Depression Inventory. Higher scores show more symptoms of depression. Construct and interpret a 90% confidence interval for the mean change in depression score. So, here are 11 subjects, and here are when they were given the caffeine pill. Now, this doesn't necessarily mean that this is the first pill, because they said they randomized the order between the caffeine and the placebo. So here just happens to be when they did receive the caffeine pill. Here are their scores on the depression and the depression test. And again, it says higher scores represent more symptoms of depression. And here are those same scores for those same subjects when they were given a placebo. So it's obviously not on a 1 to 10 scale. Now over here, these are the differences. And if you notice, I did not just take caffeine minus placebo, I did placebo minus caffeine. I just did it that way. You could do it the other way, it is completely fine. So, this Scoot. These numbers here, my difference column, these are the numbers that I'm going to end up using just like I did in the last video. So my conditions, let's just move that right there, why don't we? All right, conditions. I still have my 3 conditions. I still got to check, do I have a random sample? Well, let's see. Now, notice our 11 people, they weren't randomly selected, but the thing that was random, since we are in an experiment here, is the treatments. And were the treatments, the caffeine and the placebo pills, randomized? And they were. Okay? So in an experiment, you don't randomly select your people to be in your experiment. You choose your treatments as being the randomized part. So random, we will say treatments were randomized. And that takes care of that condition. Independent. Is the population at least 10 times our sample size? Well, our population, I would have to say, would be our people in general. So we'd say all people. Are all people greater than 110? We will assume that is true. Assume true. Which means we may calculate a standard error, sigma sub x bar, and normal. Now, we only have a sample size of 11, so the central limit theorem will not necessarily apply here. Now, with a small sample size, we need to plot our data, our differences here. And we need to look for 2 things. Number 1, we need to look for outliers, or we need to look for very strong skewness. So I have already done that. I have it hidden over here. Excuse me, words. Thank you. Again, you may use a box plot, and the box plot you may do in the calculator, and all I did for that was put all these difference numbers into list 1, and then went up to my stat plot in second y equals, and did my box plot. And in my box plot, you can see here, there are no outliers present. Now, is there some skewness present? Yes, there is some skewness present. This is much longer than this from the median there. Is it strong skewness? I would have to say not. I would classify that not as really strong skewness. And if you would rather do a stem plot, here is my stem plot here with full key. And you can see that, yes, this probably has some skewness to it. Skewed right a bit, just like we could tell from this that this is probably skewed right. But is it strong overbearing skewness? I would say not. So we will say based on our data, we may assume T procedures. So even though we're saying we're going to check the normal condition, the normal doesn't really apply. We have to replace it with its, to look alike the T procedure. So we may assume T procedures and we may use inverse T. So now, let's get to work. Move this back over here. So now here's our formula, x bar plus or minus t star times s, our sample standard deviation, divided by the square root of n. Now, where's my x bar and my s going to come from? Well, they're going to come from my data. So again, if you already have this in list 1 for making a box plot, then you could do press stat, go over to calc, and then do one variable statistics on list 1. And you will be given the sample mean and the sample standard deviation. So if I do that, I get 7.364 to 4 sig figs for my sample mean and 6.19 or 6.9177, or really I could have made that 6.918 if I wanted to do 4 sig figs. Technically I did 5, my bad. Now the t-score, the 1.812, I'm just going to kind of drop down here. I would have to take inverse t, and since I'm doing I believe I said a 90% confidence interval, yes, a 90%, then that means I have 10% in my tails, 5% in one tail. So 5% in one tail, and then I need a degrees of freedom, which is n minus 1. My sample size is 11, so minus 1. That gives me 10. So if I did that, that should give me this 1.812. It will give you a negative version, but we will chop off negative. So then, once I am here, let me erase a little bit of this. Then I get 3.7794 or 3.779, if you will, for my margin of error. This is my margin of error. And add and subtract that. And here is my 90% confidence interval. So now for my conclusion, I am 90% confident that the mean, and what was I trying to measure? The difference in depression score. For a match pair, this is where it's going to be different. It's always going to be the difference in whatever you were measuring, and that was our depression scores. And I have to specify here how I did the difference. Okay, I said to do placebo minus caffeine, so I state that right here. If you want to do caffeine minus placebo, that's all fine and dandy. You can do that. For all, our population was specifically, I guess, caffeine addicts, not necessarily people, is between our two values here. Okay, so our difference, notice here, these are all positive values. So we're saying we're 90% confident we're going to end up with a positive value. Now, positive values meant increased depression. Okay, and if we didn't think there was going to be a difference between the caffeine and the placebo, then we would expect a difference of 0. If the placebo and the caffeine had the same effect, we would expect very similar numbers for here, 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 and here. And we would expect differences that were closer to 0. But you know what? We're not seeing that. So that means that the caffeine pill does, in fact, and this is something we'll get more into next chapter, that the caffeine pills really can decrease the depreciation, except it's not depreciation, it's depression. That is how sad this video is making me. So I hope you guys learned a lot and you enjoyed all my various voices that are in my head. Stop it, Steve. Steve. Ah, sometimes the voices, they tell me to do things I don't want to do. Okay, that's all for chapter 8. Hope you had fun.